Hi. To start with, I'd like to thank the conference organizer for giving me this opportunity to present our research on elevated temperature resistance of welded tubular joints for fire safety design. My name is Yong. I'm a professor of structure and fire engineering at the University of Manchester in the UK, and this research was done in collaboration with Dr. Emre Ozyat from the University of Gümüşhane in Turkey. So this research was done, as I said, in collaboration with Dr. Ozyat when he started his PhD at the University of Manchester, working with me quite a few years ago, and followed by a postdoctoral research fellowship funded by the Scientific and Technological Research Council of Turkey. And this research was also partially sponsored by an organization called the CEDAC, which is the International Organization for Research and Development in Tubular Structures. The research title of CEDAC was a welded joint strength at elevated temperatures. So what's the context of this research? Tubular joints, welded tubular joints, are widely used to cover large spaces onshore, such as airports and factories and many big buildings, as well as offshore, for example, oil platform and even wind turbine support structures. So over many decades, many researchers have done a huge amount of research to understand the behavior of welded tubular joints, different types and different loading conditions at ambient temperature. So nowadays, design guides are available for welded tubular joints at ambient temperature. Obviously, when we're dealing with fire safety at elevated temperatures, we cannot repeat the process which happened for ambient temperature research. Simply, there is not enough resources in terms of money and people. So then we have to be very careful in what we do. In fact, if we look at elevated temperature or fire resistance, it is much more complicated than ambient temperature research. Ambient temperature, which is 20 degrees, if you think of it, is only one of many possible temperatures in fire design. So we have then to be very careful in what we do. And that then brings me to, I'm going to spend then a few minutes then talk about the methodology which we used to enable us to carry out this design to produce sufficient information for design purposes, and then followed by a summary of the findings which we have achieved in terms of different types of tubular joints, circular hollow section tubes, rectangular or square section tubes. And we carried out research on these tubes, and then we extended to so-called elliptic hollow section tubes. They were under axial brace loading as the basis of our research, and then we extended that to the same joints but under in-plane or out-of-plane bending in braces. They are both the so-called planar joints, two-dimensional joints. We later then also extended to three-dimensional joints. Here then we deal with normal grade of steel, and then nowadays there's a trend to use high-strength steel tubular joints or tubes. Then we also then extended our research to high-strength steel tubes. Luckily, quite a lot of our research the results have now been implemented in the next version of Eurocode 3, part 1.2 for fire safety design. So I will just then show you what is now adopted in the Eurocode. And finally, some general conclusions and some useful references which we have published our results. So let's then look at the background as well as the methodology which we then used to carry out this research. Normally, when we deal with high temperature structural resistance, we modify the existing equations at ambient temperature by the strength or stiffness reduction coefficients. So what is showing in this graph in here is the change or reduction in strength or stiffness of steel as a function of temperature. Here then is for the yield stress, here then is for the Young's modulus. So we use these two factors to modify the ambient temperature resistance. So what we then need to do is then to identify which factor to use or how to combine them. To do that, we then need to understand the failure modes of joints. So what is showing here are 5 different failure modes of joints at at ambient temperature. Failure modes B, C, B, D, and B is the so-called punching shear. D is the cord itself being sheared, and E is then local yield or of the cord. So these 3 failure modes, they are completely dominated by the yield stress of the material. So for these 3 failure modes, all we have to do is then to multiply the ambient temperature equation by this reduction factor of yield strength. So that's fine. That's easier to do. For failure mode C, which is the so-called side or failure modes, they behave pretty much like columns. So what we then need to do, all we need to do is then to modify the Young's modulus and the yield strength of the material at ambient temperatures, pretty much like what we do for normal column design in fire. So that's easier to do. The one that is more difficult to do is then the last failure mode, which happens to be the most common failure mode of welded joints, this failure mode A in here, where then we have the so-called cord face plastification in here. So if we then load up the brace members, either compression, tension, or bending in here, then the cord face will then deform and will reach its load current capacity. The resistance for cord face plastification is a combination of a number of considerations at ambient temperature. So we then have, of course, yield nice solution, because the whole thing then develops like a yield nice solution, as you can show in here. But this yield nice solution is also limited by some consideration of deflection limit of the cord face. So we have then a yield nice solution, which is determined by yield strength, and also deformation limit, which is then influenced by Young's modulus. But what is going on also then which complicates things is that then the final equation is really only dependent on the yield stress. So if we then simply multiply this yield stress by the reduction factor for yield stress, then we may not be safe enough, because then we have to allow for deformation mode. Also complicates things for a cord face plastification in fire is that then the geometry of the cord face might change. If you then compression in here, the face, instead of being round at ambient temperature, now becomes much fatter. And the yield nice solution is based on geometry. So if you then change the geometry, you change the equations. So here then we cannot simply then multiply the yield stress at ambient temperature by the yield strength reduction at high temperatures to extend this equation to elevated temperature applications, because there are 2 deflection related issues. One is this become fatter, and also because I mentioned already deflection limits are already embedded in this equation. So we then carried out a huge amount of analytical or numerical research to then resolve this problem. To do that, as I said, then we wanted in the end to use the material properties at elevated temperatures. I mentioned already we have the yield the effective yield stress as with Young's modulus. So we cannot simply then modify the design equation by using this factor, even though the ambient temperature equation is based on yield line solution. Because if we do that, we could be on the unsafe side, because this value is always bigger than this value, the change in Young's modulus. So we cannot then just use this factor to multiply the strengths at 20 degrees. Let's say 20 degrees. We have to take into consideration the effect on Young's modulus. So we have to then identify which of these two values use, or in some cases combining these two values. And that's really what we did. That's then determined the direction of our research. As I said, we carried out our research using simulation using Abacus, which is very commonly used. I'm not going to then bore you with all these details of how to do the simulation. Later on, if you're interested, I will show you a few references which have all the details of numerical implementation of our modeling process. So here then I'm just going to give you present the main findings of our research along the 5 things which I identified in the beginning. So let's then look at planar joints, planar truss joints, where the brace members and the cord, they are in one plane. We have different types of joints, the so-called T, Y, X, K, N, and they can be in compression or tension. So our main conclusions for this part is then that for all these joints in tension, if they all have tension force in the brace members, or if they have some sort of symmetrical joint arrangement, for example, if you've got a K joint in here, then you can have compression and tension in here. Then what we're saying here, then you can use the yield line reduction factor, yield strength reduction factor of steel to modify the ambient temperature. Because in this case in here, if we have tension or if the loading is symmetrical, then this fattening effect is negligible. Okay, so this fattening effect is negligible. So that in this case then the original failure mode is the same as the ambient temperature and the yield line solution, and all you have to do is then use the yield strength reduction factor to modify the ambient temperature equation. On the other hand, for these 3 types of joints which have compression in the brace members, then this fattening becomes really quite dramatic, and then that then influences the design strength of the joint, because this fattening is caused by deflection. So in this case in here, we cannot modify the ambient temperature resistance by the yield strength reduction factor of steel. We then recommend using the reduction factor, lower value of reduction factor for Young's modulus. So that's then the first bit of finding we have, and these are then the evidence of our results. So if we have tension, then our simulation results express as ratio at high temperatures to ambient temperature is close to this curve, which is the yield strength reduction factor of steel. On the other hand, if we don't have compression here, then the same ratios of high temperature to ambient temperature resistance are closer to the dotted lines, which is the yield line, the Young's modulus reduction factor. Obviously, the proposal in here is not exact, but then we're not seeking exact agreement. We're seeking for a safe, simple modification to the ambient temperature design equation for elevated temperature applications. So that's then the first bit of result. Then we then extended the results to so-called elliptic hollow sections. Elliptic hollow sections, then you can then join them in 2 ways, either on the fat side or the wide side or the narrow side. So depending on which side you're joining, the results are different, because this side, if you join on this side, the tube is easy to get flattened, whereas if you join on this side, then it's much more difficult to become fat, because the stiffness to resist movement is much stronger. So in that case, then the change in geometry is not as big, and that is then borne out by the finding of our simulations. So if we then have the joints compared on the right side, the results tend to follow the Young's modulus reduction factors, because the geometry change is much easier, or is more prone to flattening or ovalization. So then we have to use the Young's modulus reduction factor. But then on the other hand, if we then have on the narrow side, then it's much more difficult to move sideways, deform sideways, and then the results or simulation results tend to agree with the yield stress reduction factors as we expected. Of course, then if we have under tension the brace members as before, then they will follow the yield strength reduction factor. That's what I'm saying in here. If tension, then they follow the yield strength reduction factor. So that's then the extension to elevated temperature resistance of elliptic hollow section joints. We then moved on to then investigate various joints under bending. So we have bending in plane. We also bending in the other direction, out the plane. If we then think about bending, of course, we carried out our investigations at various temperatures with different types of joints. If we then think about bending, bending is really just then part, let's say if we then have bending in here, then one side in compression, the other side in tension. So as we said before, for each joint under tension, we normally then modify the ambient temperature design equation by the yield strength, because tension, and under compression, then we modify the ambient temperature resistance by the Young's modulus factor. So then when the bending in here, then we say, well, it's half-half. So in the end, we then recommend using the average of the yield strength reduction factor of Young's modulus and yield stress to modify the ambient temperature resistance equation to calculate the value for elevated temperatures, and which are these values or simulations, they are pretty close to the average of these two lines. Again, we're not seeking exact agreement. We're trying to find a solution which is safe and simple for design purposes. So that's then under in-plane bending for circular hollow section tubes joints, but the results are the same for other types of joints. And then that's then under out-plane bending in here. Again, the results can be safely predicted by using the average of Young's modulus and yield strength reduction factors of steel. And then we did the same for elliptic hollow section joints and the in-plane bending. Again, the results are best expressed by using the average values of Young's modulus and the yield strength reduction factors. So that's then under bending moment, but all of them under tension, compression, bending in all these joints, we carried out our simulations using normal steel, for example, S355, S275, and to some extent S460 as well, because for these types of steel, the reduction at high temperatures in Young's modulus, the reduction is lower than in yield stress, or there's more reduction in elastic modulus than in yield strength. So if we then use yield strength as reduction modification, then we may not be on the safe side. For high strength steel, on the other hand, the reduction factors in Young's modulus, if you then look at compare then the reduction factors in yield stress, all these values are bigger or not less than the reaction factors in yield strength of steel. Therefore, if we then multiply the ambient temperature resistance by the Young's the yield strength reduction factor, that's the 20-degree resistance, by the yield strength reduction factor, then we are going to be on the safe side. And that then is really our proof of results. So when we carried out, repeated our simulations before using different grades of steel, high strength steel, and then these are really our results in here. So we've got compression in here, then all the results, they follow the reduction factor for yield in this case, because the reduction factors or retention factors for yield are lower than the retention factors for Young's modulus. So that's Young's modulus, this is the yield. So we can then, for high strength steel, because of this different trends of change at high temperatures, we can then use the modification factor at high temperatures for yield strength, and that's safe enough. So this then has more results in there, and the bending as well, the same trend, following the yield strength reduction factor, rather than influenced by Young's modulus. So that's good, that's easy to do. The next part of our research then is to extend our work to the so-called double K joints. They've got K joints in two different directions of three-dimensional structure. We use the so-called gap joints, which is most commonly used. So there's a bit of gap between the brace members. With this type of joints, it depends on whether the gap is big or the gap is small. When the gap is big, then each individual chord is almost acting on its own. When the gap is small, then the two of them then almost like acting as one. So that's the first way you have to do. Of course, for ambient temperature design, there is a definition of what is big gap, what is small gap. And then we carried out research to then say whether the same definition can be applied to high temperatures. And these results are showing there that then, in fact, yes, we can then apply the same definition at ambient temperature to elevated temperatures. This is then where the definition of small gap and the big gap, and then the failure modes are different. So as you can see in here, at high temperatures, the failure modes for small gap and the failure modes for large gaps, they're pretty much the same at ambient temperature as at ambient temperature. So that's good. Then for large gaps and small gaps, again, we're trying to find out the modification factors for strength. Which modification factor should they then apply to the ambient temperature resistance? Looking at large gaps, as I say, then large gaps, because the gaps are large, each individual brace member is almost acting individually. It's almost acting individually. Therefore, as I said before, if we then have compression, then we use the Young's modulus reduction factor, which is this. On the other hand, because even though the gap is big, what is behaving under this brace load on this part of the chord is also then affected what is going on by the chord in the neighboring brace member. So there is some effect in there, meaning then the effect that we found for individual brace member in planar joints is limited or restrained by what is going on in the neighboring joint. So we're not as bad as just changing according to Young's modulus, which is lower than yield strength. There is a limiting factor in there, or is not fattening as much as under one brace member. Therefore, then we found then approximately the strength reductions at high temperatures are higher than that. In fact, they're a bit closer to the average of these two values, yield stress and Young's modulus. And that is then when we have equal compressive forces in wall brace members, or when we have opposite brace forces, because this could happen. So what we then recommend is then for large gaps, we use the average of these two values to modify the ambient temperature resistance. On the other hand, for small gaps, then depends on what the loads in these two brace members, whether they are opposite or whether they're in the same direction. If they're then in the same direction, then these two brace members together, they actually then combined, acting as just like one. In this case in here, then the reduction factors are closer to the Young's modulus, because then the whole thing acts as one. On the other hand, if we then have totally opposite values, then as we found before, just like any bending in there, we take the average between yield stress and the Young's modulus. And then of course then when the ratio of this force changes from total opposite, equal opposite to the same compression, then there is a transition period of linear. So that's then what we found out in the end, which then becomes quite easy to implement in design. So that's then the summary of our research. And finally, as I said, we have now managed to implement our findings in the next version of Eurocode 3 Part 1.2 for elevated temperature resistance of tubular joints, because in the current version there is no design method for tubular joints at high temperatures. So then we have implemented the result. What we have implemented in there is then planar joints, two-dimensional joints, which are still used in quite many cases under normal using normal grades of steel and axial load as well as bending moments. Our research on three-dimensional joints were not available for implementation in the Eurocode, but that's easy to implement in future. So that's then coming to the conclusion now. As I said, tubular joints have received a lot of research at ambient temperature. We cannot then repeat the same process at elevated temperatures for fire safety design, because the behavior is much more complicated than at ambient temperature, and we just don't really have the resources to do that. Therefore, then that forced us to understand the failure modes of joints, as well as what we need for design purposes. So having understood that, then we devised a line of research to achieve our design objectives or our research objectives for deriving simple and safe design equations for elevated temperature applications. So what in the end then we have is then, depending on the joint mode, failure mode, we then have recommended modifications of either using yield stress of steel or Young's modulus of steel, or combination of them to modify the ambient temperature resistance. And as I said, part of our research has now been implemented in the Eurocodes for fire safety design of steel structures. Finally, just a few references for you to take away. So we then have published our research for tubular joints under axial load, and then also then extended that to elliptic sections. We then also then implemented this to bending moments as well as to three-dimensional joints. And with that, thank you very much for your attention.